Consistency. It's related that, it's an outgrowth of atomicity. Transactions leave a database in a consistent state. So you never end up with the data in a database being corrupted with respect to certain properties you might want to enforce. And I'll have more to say about that later. There's isolation. Because databases are shared among multiple programs, isolation means it looks to you like you're the only one using it. The different programs don't interfere with each other when they're using the database. And durability, the results of committed transactions will not be lost. Once you change the database, it's permanent. And databases make this work by constantly, like I said, they back themselves up. Back themselves up off-site, replicate themselves. So those are the goals of relational database systems. Now, the database we're going to be using really, it certainly won't have the durability property in that if your laptop gets submerged, you're going to lose your data. You're not going to be using one that's replicating the self-load data. But it does have, atomicity and consistency and isolation. So there are a couple choices we could make when we add database to your service. One would be to use some database that's on cloud. So you can go to Amazon or Microsoft or whatever and pay them a monthly fee and have a database that's hosted on their cloud, and then you can use it in whatever program you want to use it. Okay? We could do that, yeah?
For durability, I mean, obviously in order to have that, you're backing up the information to a database or to an actual hard drive or another, like, solid-state memory that's persistent. Yeah. Okay. So durability you get first of all by replicating it. On a large scale, it's replicating it to independent databases. But locally, yeah, you get it by your data. Your data is ultimately written to a hard drive. So one way to do durability is to back up a hard drive. Okay. So then my question would be: is that anytime you write to a hard drive, it may become corrupted if something goes wrong, for example. So does that put any of the other three properties of a database?
Well, not if the relational database is properly designed. They're designed to deal with a disk failure. Before it writes anything to the disk, it writes a log of what it's going to do somewhere. And then it starts writing to the disk, and if that write fails, it can back up to where it was at the beginning to replay the log.
Kind of like a RAID array, when this fails, you still have enough to recreate the information.
Yeah, there's always enough information around to recreate what you lost. So you don't start changing anything in the database until you have saved away what it is you're about to do, so you can redo it if necessary. So what we'll be using instead of using an actual database server is basically Visual Studio has built into it a very simple database program. And it operates off of, it keeps its state in files inside your solution. So the entire state of the database is inside Visual Studio. You'll be able to send it up to GitHub under version control. So I guess that's one way you can get durability. And the price you pay is that it's not accessible from anywhere else. It's not a server. It's not a server you can access via the web. It's just accessible only by your program. But that's all that you need. Then when you get it working, after you get your database version working, we'll have a lab where you'll see how you can take this local description of the database and your code and send it up to Azure, which is Microsoft's web cloud service. And with very little work on your part, there's no new programming required. You can take a working application in Visual Studio and just migrate it up to the web, and then you can access it via URL somewhere else. So we ultimately will migrate to a real database and a real server. Okay, now, like I said, a database system is typically a server that has multiple users and multiple databases. And a synonym for a database is a schema. And a schema is a plan for how you organize the data. In a relational database, all your data is put into tables. So table and relation are synonyms. And so when you want to design a database, for an application, you basically decide what tables you want and what information is in each table. So that's database design. And doing this properly is a science, a mathematical science. There's a mathematics of how to do it correctly that we won't go into. You can take a database class and learn about that. We'll sort of approach it a little more informally. But this is an example of typical data. Suppose you wanted to keep track of people's names and their ID numbers and their date of birth. You could create a table that has those pieces of information in it. And every time you want to add a person to the database, you add a new row to this table. So you add Dumbledore, ID 5 Dumbledore, and whatever Dumbledore's birthday is. So that would be a single table schema. So in terms of using Visual Studio or using a database system, what you would do is, before you start using it in the program, you would go in and you would specify the table. You say, I want a table, there's integers here, there's strings here, there's dates there. This is what the columns are called. And you describe it, and then you would be able to start adding data to it. So database design comes down to figuring out what tables you want and what goes into them. So as an example, let's talk about creating a database for a library application. So, like the public library. We need to keep track of the names of the patrons that use the library, their library card numbers, their phone numbers. We want to keep track of all the different book titles we have, and along with we need the titles of the book, the authors of the book, the serial numbers of the book. We've got to keep track of the books that are checked out. Now I mentioned there was a mathematics. It's called normal forms. These are some of the basics that you want to get out of the mathematics. We want, generally, the entries in tables should be atomic, not compound. Now what does that mean? What does it mean for data to be atomic? Yeah?
It doesn't.
Back there.
It'd be like, instead of storing, like their date of birth, you would store like how many days from the day they find out they are old or something like that?
No, it doesn't. Atomic in this case doesn't mean primitive. It means indivisible. But what does that have to do with data? Yeah.
The smallest unit, like if you had an ID, you would want to like do numbers and like a string to describe it.
Okay,
Like
right.
The smallest unit.
So going back to here, you could imagine having one column, and it's the string that contains one, a space, Harry, a space, and then the date. What would be the problem with storing it that way?
It'd be hard to query.
It's hard. So it's hard on several levels. Anytime you got data out, you then have to turn around and extract what you really wanted from the string. If you wanted someone's name, you have to get the whole row and pull their name out. And suppose you wanted to ask the database, what is Harry's date of birth? All right. This way, if you want Harry's date of birth, it can go find Harry in a column, find the corresponding date of birth, and return it. If it's a string, you're making the work of the database harder. Yeah.
So is atomic like the smallest reasonable question someone would ask the database?
It's the smallest reasonable piece of data that the database would give back as an answer to a question. Now you might ask, is this atomic or not? Right? It's really three things: month, day, and year. And it really just depends what you're going to do with it. If you're going to have a lot of queries to the database asking it, show me everyone that was born in 1980, maybe you want to split out month, day, and year into separate columns. Or maybe not. It's sort of a point of view, but as to what's atomic and what's not. But clearly, if you mashed all these together into one thing, it's not atomic anymore. Okay, so we want to store atomic data. We want to avoid storing the same information twice. So the fact that Harry was born on whatever date, that should only be stored once in the database, not multiple places. Because if it's in multiple places, then it becomes sort of a maintenance problem. They can get out of sync, right? If you change it in one place, you may forget to change it in the other. And the other is we want to avoid having to store nulls. So let's try. Here's an idea. Here's a bad design for the database. So basically, I'm just putting I'm making a column for everything. Name, phone number, card number, titles, authors, and serial numbers of books. Think of the serial numbers being like a ISBN, a unique identifier for, like Profiles in Courage. We got multiple copies. All your Profiles in Courage are 1005. What's the problem with this representation? Yeah?
We wouldn't be able to get all of the data back because no column is filled.
Yeah, so they're nulls.
Yeah.
Now, why are there nulls? Why did I put nulls in here? I mean, what does it even mean here? What does this line of data tell you here? Yeah?
Dan has checked out the good soldier.
Right. Dan, who has this phone number and has card number 4, has checked out the Good Soldier, which is written by Ford and has serial number 1006. Okay? This also says that Dan, who has this phone number, he has 2 phone numbers, has card number 4 and has checked out the same book. So how does this violate, how do these 2 rows violate my goals? Yeah.
Store the same data twice.
I had to store the same data twice. Because what's new here is that Dan has 2 phone numbers. But have a row for Dan, every row is going to contain, we have to, you know, we can't just say Dan has this number. We have to say what book he has checked out. So we're storing the same information twice. Like the Good Soldier is written by Ford, or the Good Soldier has serial number 1006. Like up there, we have these books, 1002 and 1003, that no one has checked out. So we have to store nulls because no one has them checked out. That's just all, you know, you look at that, it's just confusing on the face of it. So that's a bad way to store things in tables. To meet our goals, we need to break our table down, break our single table down into multiple tables. So here's a better design. So let's look, I have multiple tables. Let's look what they're for. We have a patrons table, and it just matches, it gives the names of the patrons and their card numbers. So patrons just associates people with card numbers. Phones associates card numbers with phones. Now why not just add a third column over your phone? Store card number, name, phone. Yeah.
So a person can have more than one phone number?
Because a person can have more than one phone number, and so if we stored phone numbers up there, we'd be duplicating the card number information for that person. We don't want to have duplicates. So we split it, so we got one table holding card numbers and names, another containing card numbers and phones. And we can, yeah.
How is that not duplicated?
What's duplicate?
Well, you have 2 4s in there. 4 phones.
Well, there's 2 4s. I'm not saying you can't duplicate strings or numbers or whatever. What's not duplicated is the relationship between 2. Okay? So the fact that 4 has that phone number and 4 has that phone number is, there are 2 different pieces of information. Whereas if we tried to put it over here, we would twice be saying that Dan's card number is 4. Okay? Let's see what else there is. We have titles. So these are all the different titles we have in our library. So we have the book ID. So what I said before was wrong. This is more like the ISBN. A unique number for Harry Potter. Even if you have 10 copies of Harry Potter, they're all going to have the same book ID, same international book number. So we've got 5 different books in our library. And for each one we store its ID number, its title, and its author. Now what's the catalog doing for us? How's that different from titles? Yeah?
Are you saying that there's 2 copies of Harry Potter? So
Yes.
2 different people can check it out?
Right. So it shows up there in the right-hand column. See, 1001 appears twice. So that means we've got 2 physical copies of Harry Potter, and they have different serial numbers. And each can be checked out or not. So those are the books, the physical books that we have. These are the titles of all the books that we have. When you're looking at the online information, you're interested in this. You want to know what books there are. When the library is keeping track of what books are out, it needs that information. Okay, so we got that, and finally we know what are checked out. This says that card number 1 has that first copy of Harry Potter checked out, and so on. So there are no nulls. We're not duplicating relationships anywhere. But what's the cost? Yeah?
I'm getting really hard about how to make these tables and how to divide up the data so that it's going
Okay, so yeah, doing the design in the first place is tricky. Takes some experience. Yeah?
If you want to find out like what book Joe has checked out, you have to check this table, then jump to this table, then to this table to find out.
Okay, so if I want to know what books does Joe have checked out, let's see what's involved. I have to go to Joe, I see it's card number 1. I come here and I see card number 1. Say I want to know the titles of the book Joe has checked out. So card number 1 has 1001 checked out. 1001 is book ID 10001, and that's Harry Potter. So I report Harry Potter, and then I have to look here, 1005. That's 10,004, so that's Profiles in Courage. Seems like a complicated program to have to write. But, yeah.
So notice, in everything except patrons, you're saying, look at the far left column and then get your answer. But for patrons, you're doing it backwards. Is that?
Just because the input was Joe, so that's where I had to start. I guess it's just a coincidence. But here's the deal. Suppose that I gave you these tables. They're in your program in C#. So they're like a bunch of arrays of different kinds of objects. And I ask you to answer a question like, what are the titles of all the books that Joe has checked out? What would your program look like? Got an idea? Yeah.
Select from table.
Well, no, you're telling me what it looks like in SQL. But suppose you weren't using the query language. What would just native C# look like?
Use link to get something similar to it.
Okay, yeah.
Would it look like a bunch of nested for loops?
Yeah, it'd be a bunch of nested loops. You'd be looping through that table looking for Joe, and then looping through this table looking for 1, and then looping through that table looking for something, and looping through this table. You'd have a bunch of nested loops with conditionals, and you'd be hating life. But that's not how you'd be working. Instead, what we'll see is that when you want to get information out of a database, you don't write a program to loop through tables to find it. You describe at a high level the answer that you want. And the database takes care of doing the looping to pull the information out. And the database is going to be a lot faster than any program you could write. It's so highly optimized. It's going to be much, if you tried to write the same programs to execute the loops to get the data out, it will be slower than what the database will produce from the query that you give. Yeah?
Now, does the databot base use hash tables to make this fast, or what does it do?
The database uses a variety of technologies to make it fast. A very common one is called a B tree, which is like a binary tree, except the nodes are pages in memory. And they're not binary. They might have like 100 children or something. But that doesn't really matter. When you take a database class, you learn something about what's going on behind the scenes. I'm just telling you that there's a simple way to express the question. You send the question, it's called a query, to the database system. It compiles it into actual code that extracts the answer. So you're working, the queries are non-procedural. You're not describing how to extract the answer. You're just describing the answer that you want. And you leave the database to figure out how to pull it out efficiently. Right? Now we'll look at queries next, but I just want to finish up this group of slides. So there's our design, and we're going to be using this throughout. So we'll come back and look at it later. You're going to be, in the lab tomorrow, like I said, you will create a set of tables to represent the information needed to keep track of boggle games. And that, if I remember correctly, is a 3-table solution. So you'll be seeing what those tables are. You don't have to use my approach, but if you don't have a better idea, you might as well. You'll see what the tables are and how to define them in your solution. So last thing I want to show you is some of these things up here are entities, are called entities, and some are relationships. So some tables contain information about things, and some tables contain a relationship between those things, among those things. So I gave you a preview there briefly, but what are the entities here? What are the things? Yeah?
Patrons and titles.
Okay, patrons, so patrons are things, or patrons are things, titles are things, and actually phone numbers are things. So those are our entities. And the other two tables give relationships between the patrons, the phones, and the titles. Actually, between the patrons and the titles. So that, this has information from one table, information from a different table, and ties them together. Similarly here. So you see, this just contains sort of artificial information that's used to keep track of things. This is the actual stuff that you would care about, that you'd ask about. Okay? So that's called, sometimes you hear about entity relationship diagrams. Well, I won't go into that. I just wanted to explain the difference. So that's just that's our same design back there. So let's take a break and we'll finish this up and then actually do some queries. All right, let's get started again. All right, so when you describe your database design in Layout tomorrow, you'll first of all be creating tables, and you'll say the name of the table, and you'll give the name of each column and the type of data that goes in each column. That's part of it. And then you give various constraints on those tables. So what are some things you'd never expect to see in the patrons table? Can you think of any, like a row you would never expect to see?
Titles.
Well, other than, there's going to be an integer and a string, some combination.
Oh, I was going to say type of dinosaurs.
Well, someone's name could be Brontosaurus, I guess. Yeah?
Negative numbers.
Okay, you might not expect to see negative card numbers, or actually what I had in mind is you wouldn't expect to see duplicate card numbers, right? You wouldn't expect to see two people with card number 4. So that's a constraint, and we naturally have that expectation. You can describe that constraint. You can tell the database system, here's a constraint. And the database can do two things with that information. It can, once it realizes that card numbers are unique, it can create indexes, and it can create efficient indexes to look things up by card number. And also, if someone ever tries to put in a duplicate card number, it can refuse and complain and say, no, the card number has to be unique. So it can both enforce the constraint and take advantage of it to make operations faster. So there are several constraints that you can describe when you're creating your tables. That's what we're looking at next. Yeah?
Can you do a constraint that has to do with more like pattern matching? Like I need a name with a capital first character?
Typically, no. They're not that low level. Okay. It's more, you can have constraints that involve more than one column. So let me just show you what constraints there are. So usually for a table you want to describe its primary key. So a primary key is some column or combination of columns that are going to be unique on each row. So what would be a reasonable primary key for this table? For titles? Book ID. So you would just, in the design, you would say book ID is the primary key. And now, that's what we were saying before. It's going to complain if you try to put in a duplicate book ID. And it's going to take advantage of the fact that this is unique. make it very efficient to look things up. On the other hand, over here, clearly, card number is not the primary key, because here's 2 4s. Phone number is not the, it looks like it could be here, but why would phone number not be a primary key? Yeah?
You list your house phone number and you've got 3 people with library cards in
Right.
the house.
So you have a house phone, multiple people that share the same phone. So what if you wanted to give a primary key for this, there are 2 options. One is, what a lot of people do is add a 3rd column over here, which basically is a unique number for each row, and use that as a primary key. Another thing you do is just say the combination of card number and phone is the primary key. Because you would never expect to see 4 and then this number and then 4 and the same number again. So that's what a primary key is. It's a kind of uniqueness constraint. Yes?
Does a table require a primary key?
No. It doesn't require a primary key. So you could leave it off of that but not really see any. Yep?
Do you have database management systems that normalize the data? Like if it was given like JK rolling, you would only store rolling or something? And it would have like a normalization system to store certain aspects of the data in a uniform way.
So are you asking or asserting?
I'm asking like if that is something that is
Well,
Can you repeat the question?
he's asking could databases have normalization procedures where if you might say that if someone tries to store JK rolling, it just stores the last name. I suppose that's possible, but it's not I wouldn't say that's a common feature of relational database systems. Okay? So those are primary keys we could express. It's also possible you might have more than one column that's unique, or more than one combination of columns that are unique. And you could also note that and say those are just different uniqueness constraints. You only have one primary key, but you can have other keys. You can describe an integer valued column as being an auto increment column. So this would be an example. You might set this table to be auto incremented. What that means is when you add a new row to it, you would just give the title and the author. You would not give the book ID. The database would generate the book ID. And what it typically does is it just starts somewhere and then adds 1 each time. It needs a book ID. So rather than you having to generate unique numbers, you can let the database do it just by labeling the column as auto increment. And finally, there are foreign key constraints, which are the most complicated. There are constraints that relate to tables. And it happens when a column in one table contains data that appears in another column in a different table. So for example, over here, what would you expect about all these book IDs? Yeah?
That they exist.
That they actually appear over here. You wouldn't expect to find a book ID here that doesn't appear over here. You know, if you don't physically own the book, it's not going to show up in the catalog. So you can tell the database that as well. You can say, if an attempt is made to add a row that contains a book ID, which does not occur in this column of this table, all I do is brush this thing. Then that's a mistake that it can flag. Yeah.
Can you make it such that the titles cares that exists, or I guess that it goes one way but not the other? That like
Yeah, it's one way.
Okay.
So basically, you're saying over here that book ID that this book ID is a foreign key for this. Everything in this column must appear in this column. Now, one way you could violate the constraint is by inserting something in there that violates the constraint. How else could you violate the constraint if you're modifying the tables? What's that? What if you deleted this title? Suddenly there's an orphan 10,005 over there. Or, what's another thing you could do to screw things up? Yeah?
Change the book ID in the left table.
Right. Say we change this to 10,008 for some reason. Suddenly, same problem, 10,005 is working. So there are various ways these constraints can be violated. And you have your option when you design the database as to what you should do when it happens. So one thing you can do is you can say if something is being done that's going to violate a foreign key constraint, you can say, tell the database, don't allow it. Just don't do it. That's the first option. Another is to cascade the change, which says, okay, if you delete this, if you delete 10,005, you got to come over here and delete every row that has a 10,005 in it. Or if you change this to 10,008, you got to come over here and change it to 10,008. Or another option you can pick is just to null out the problem. So if you delete this, you just store a null here. I don't really like that solution. Things to be said for the first two choices, though. So you can choose. And you can have different things to do on deletion or on insertion or on update. You can take your choice. So anyway, those are constraints you can express, and you'll be getting some experience with them tomorrow in the lab when you create your tables. So now we're going to turn to the query language that are used, that we're going to use to get information out of the database system. So we assume the database exists and there's data in it. We're just interested in getting information out for right now. And what we're going to use is a language that's very commonly supported in relational database systems called SQL or SQL, depending on what you heard when you first learned it. I tend to say SQL. SQL has fewer syllables. It stands for Structured Query Language. And every vendor has their own slightly different take on SQL. Like Microsoft's version, Oracle's version of SQL are going to have slight differences. But the differences are sort of way off in the corners. A very popular open source database management system is MySQL. So it's free. You can get it run on a dedicated machine, access over network, so it's a true server system. And you can have a client that you use to manage the database with. So that's a choice when you need a full-blown database system on a free one. That's a very commonly made choice. Microsoft's version, we're going to be using Microsoft versions of the database system. Its query language is TSQL. I couldn't tell you the difference from standard SQL. This is a link, one place you could go to learn SQL. And I already mentioned that we'll be using a simple local database. Now, does anyone know what the most commonly used database system is? Yeah?
Oracle?
She said Oracle. No. Yeah?
SQLite.
Yeah, SQLite. So SQLite isn't a server system. It's a simple database system that keeps its data in files, manages files for you. It's designed to be embedded in programs that need to maintain some state. So basically, your browsers, right? They have to maintain state. They got to keep track of all sorts of things, histories and preferences and whatnot. It uses probably an SQLite. Firefox does an SQLite database built into it. So it'd be like just a library you plug in, and it keeps the data inside the application. They're in files. Very simple. Probably a lot of the apps on your phone use a database like that. So you never see it, but it's probably in most of the programs that you use. Okay, so we're going to be using this simple database that's built into Visual Studio, which actually, come think of it, it's a lot like SQLite in that it's file-based. Now, to learn to use it, you'll be learning how to manage it tomorrow, how to set up files and stuff like that. We're going to learn how to query it today. And the rest of these slides are examples of queries you can write, but I'll leave the slides unlooked at because we're going to do the same thing over here in actual Visual Studio. So we'll do the live querying. So let me close this down and bring up Visual Studio here. So in Visual Studio, I created a project called LibraryDB. It has no code in it at all. It just has this library.mdf database that I've created. So you'll see how to do that tomorrow. So it's just an empty project with a database in it. In that database, I have pre-configured it to use the schema that I showed you before, with the patrons and the checked out table and so on. So if I double click on it, then it opens what's called the Server Explorer. So you can, in Visual Studio, you can be contacting multiple servers at various times. Server Explorer shows you all the servers that you're connected to. And right now, it's just showing me library.mdf, this local database that I'm connected to that's over there in the solution space. And under here, I can see tables and so on. Tables is all that matters to me. And if I click here on this little triangle, it'll show me that I have 5 tables: catalog, checked out, patrons, phones, titles. If I click on one of them, like, let's say patrons, so I double clicked it, it opens it up here. It's going to take a minute to initialize. And this is what you'll be seeing tomorrow, is you'll be taking this view when you design your database. So unfortunately, it's expanding this part. It's putting this part to 150% instead of that part. But what do you see up there if you can read it?
Card number and interview.
Okay, so you've got, it's showing you what the columns are. There's a column called card num, which is an int. And there's a little key to the left of card num, so that's the primary key. There's a name, which is varchar 50. That means it's a string of length at most 50. So that's just telling you what the table is. This code here is the SQL code you would write and execute to create that table. So you don't have to learn to write this stuff. That's generated for you. You sort of graphically design the table, and it figures out how to create it. So anyway, the tables are created. So we just need to use it. So to use it, I'm going to come down here to the database. I'm going to right-click on it, and I want to say New Query. And it creates a place up here where I can start typing queries. So that's how we'll learn about queries. We just type some. You use the select statement. So select. When you say select, you're asking, you want to get information back from one or more tables. I want to get everything from patrons. This is about as simple as a query gets. So what I'm asking for is give me every column and every row of the patrons table. And then don't click up here on start because there's no code. There's nothing to run and it will complain. This little check mark right here, this check mark icon will tell you if you made a syntactic error. So I'll check it and it says it's legal. Now I'll run it. And when I run it, it puts the answer right here. So it gave me everything back, gave me every row, every column back from the patrons table. And you can see there are 4 rows, the 4 card numbers, the 4 names. Now, if you're writing a program, and you will be writing programs to access a database, your programs will actually contain, as strings, queries like that. So there is no different API that you use to construct your queries. Your program might literally contain the string select star from patrons. And what you have to learn is there is an API that says send this query to the database, and it gives you a way to iterate through the answers you get back. But you will be writing those queries directly. And this is as good a time as any to tell you that when you get to the point of writing queries next week to extract information from the database, you definitely want to write those queries first here. You want to debug them here. Make sure they work here before you take them and paste them into your program. Because that's just a lousy place to debug a query, is in a C# program. Debug them here in the query analyzer. Okay. Well, let's think of simple changes we could make. Right now we're getting back both columns, all rows. What's something else we could do? Yeah?
Just get the names.
Okay, let's suppose we just wanted the name of everyone in the database, everybody in the patrons table. So the star says give me all the columns. Let's change that star to name. That just says give me the name column. And so when I execute it, I just get back Basically, it's giving me back a table, but it just contains the name column, no card information. Okay? What if we want name and card? Do it that way. Information, is it card num maybe? All right, we do it that way, we get the same information we did before, except the columns are a different order because we asked for them in a different order. Okay, so you can ask for a subset of the columns. Yeah?
What if you wanted to alphabetize the names? Like get the return be alphabetical?
Okay, let's see, I think it's sort by name. Sorted? Order. Order by name, thank you. Okay? All right, so we just add that to the end.
Nope.
Oh, wrong side.
Left side.
See, that's why you don't click there. Click here. And then that happens. Yeah, I told you not to do that. So I'm going to copy this and let's see what I got to do to recover. I'm going to kill that thing. And I'm going to go to Server Explorer and restart. And now it's got an X on it. Just reopen it. Click here. There we go. And bin banjo. And I can say order by name. What is it? D-E, S-C, in descending order.
Left.
And they get sorted the opposite way. So that's when I say it's non-procedural, we're not giving the code to sort. We're not telling it how to go find the rows that we care about or the columns we care about. We're just saying what we want. It figures out how to do it efficiently. We don't have to figure out how to do it efficiently. Okay? What if you don't want all the rows? Maybe we just want the ones that come in the first half of the alphabet. So we could say where name is less than the string n, let's say. Let's see what happens when you run that. That didn't work.
Everything is less than n.
Everything's less than n. Okay.
Okay.
Let's do less than e. Yeah, we just get and, bin, and dan back. So that's a selection with a where on it, where you can say what, you know, that lets you narrow down the rows. Yeah?
Can you do an example where you only show us the even numbers?
Okay, so I want the card numbers to be even? Yeah. No. I don't do enough of this to have this all memorized. That's not going to be like that. That's a wild guess. That can't possibly work. No, I'd have to look it up to see if it's even possible. Okay? So clearly, to make good use of this, you gotta, you know, I have to Google all the time to do it because I use it so rarely to find out the exact syntax you can use. You can get really good at this to where you can express really complicated things. What you're going to find out is suppose you didn't want to learn SQL at all. You could go to that extreme and you could just, all your selections could be of the form select star from table. And so if you want to get information from a table, you pull the whole table down and then you write a loop to iterate through it and grab out the data you really want. So that's sort of the, you're working in C# now. On the table you get back from the very simple queries. On the other hand, you could learn some SQL and write a very precise query that generates just the data that you want on the database and sends you back just what you needed. Then there's no post-processing due in C#. So you sort of got your choice. I'm at the point where, you know, I can do simple things on the database, and then I might have to do some other stuff in C# because I'm just not willing to learn that much SQL. But It's a good skill to have, to be a good SQL hacker. Was that all we want to do with our database? Is take tables and cut them up, get rid of columns, get rid of rows? What else do we need to be able to do? We got to be able to combine, get information from multiple tables and combine it. Okay, so we got the catalog in the phones. I would like to find out Dan's phone number. Okay, how can we write SQL to get Dan's phone number? Now, one way we could do it is we could say select star from patrons, select star from phones, get both tables back, and then go to work in C#. But let's do it in SQL.
I googled how to do even.
Okay, how do we do that?
You do MOD, then parenthesis, order, or then card number.
Oh.
Let's see where. In here it has order ID, comma 2, then equals 0.
Okay. Ah. Well, this is TSQL, so.
Oh, so it didn't work on this.
So that didn't work. Anyway.
I think TSQ actually has just the modular sign as the other ones, so
Yeah.
just the percentage. I'm not sure.
Yeah, well, anyway, leave that as an exercise. Okay, so I'm going to sneak up on this. We were trying to find out Dan's phone number. So first of all, I'm going to say select star from, and the two tables we care about are patrons and phones. So I'm just going to say patrons, phones, and I'm going to execute that and see what we get. And this is what we get. I'm having trouble with that. Okay, so we end up with a whole bunch of rows here. So for example, it says 1 Joe 1 5555555. It says 1 Joe 2 666 6666. What has it done? Yeah.
It's combined every entry in phones with every other entry.
Right. It took every row from the one table and matched it up with every row from the other table. So we had 4 rows in patrons, and we had 5 rows, I think, in phones. So we got 20 new rows. This is called the union. It's useless. Because there's no relationship between these first 2 things and these second 2 things. It's just saying that this was a row in the first table, and that was a row in the second table. It means nothing that they're next to each other. We need to put a where in here to throw out, to keep just the ones we care about. Which of these rows are interesting?
The name and the phone.
Where the card numbers match.
We only care about the rows where the card numbers match. So like right here, this row that says card number 2 and card number 2 that, 666, so on. That row tells us that Ann's phone number is 6666666. So I want to say where, I have to say it this way, patrons.card number equals phones.card number. So that says take the union, but only keep the ones where the card numbers agree. Those are the ones that are sensible. And that's called a join. And what we end up with is this nice table that shows us for each person their phone number. So we only kept the 5 rows where the card numbers agreed. Now, I wasn't interested in everyone's phone number. I just wanted Dan's. So what can I do just to get Dan's phone numbers back? I can say and name equals Dan. So let's execute that. Okay? And actually, I didn't care about the card number or the name. I just want the phone numbers of Dan. What can I do about that? Right. Instead of asking for every row, every column rather, I'll just say, give me the phone from the result. So I'll execute that, and I just get back Dan's phone numbers. No more work required. So that's an example of a query where we're just describing what we want. You know, take these two tables, join them on card number. In other words, just batch up the rows where the card numbers agree. Throw away all the rows except the ones Dan is on, and then just give me the phone number and what's left. So that's a fairly complex operation. It's going to involve some loops. Imagine these tables are gigantic. You know, some loops, some conditionals, and so on. But we let the database worry about how to do that for us. We just describe what we want. That's how to make effective use of SQL. Yeah?
So to show like each number and then the name associated would just be phone, common name.
Right.
Right there.
So if I do that, I'm going to get the phone and the name. If I don't care about whether it's Dan, if I want everyone, I take that out. And I get phones and names. So after the select, you're saying what columns you want. Name, by the way, you see it's highlighted in blue. I'm remembering now that's a bad choice for a column name because it actually has a meaning in SQL. So that's a poor choice. I should change the slides, change this someday. It'll screw you up in some context. But anyway, you give the column you want, the tables to get the information from, and what restrictions the row should obey. And that's a select. Okay? Now over here I have queries I've run in the past. The problem is it's kind of a pain to run them because they're not associated with the database, so I'll just have to copy and paste, but let's see what they are. So that's one we've seen before. That selects everything, you know, from all the books in the database. That just selects the one column. We've solved that example, an example like that. What's that going to do? You read that? Yeah. Yeah, you.
An ordered list of all author names that are before Seuss in the alphabet who've also written a book that comes after R in the alphabet.
Okay. So you're getting all the authors as long as the title of the book comes after R and the author comes before Seuss. And then we're going to order them by title in ascending order. Right? So you just non-procedurally describe what you want and the database deals with it. Okay, there's an example of the union that we saw. Okay, there's the join that we looked at. That's where it's combining phones and patrons and making sure the card numbers agree. Let's see what this is doing. It's that join where we're choosing which columns to see here. Card number, name, and phone. I know there's a new one in here somewhere. Here, we're joining those tables, ordering by name. Okay. This is a complicated one. I might as well run it and show what it does. I don't think you have to do anything like this. A query that complex in your Boggle server. I'm just trying to give you an idea of what's possible. So this says, we do the selection, we display card number, name, and count of phone from those two tables where the card numbers agree, and it says group by card number and name. Anyway, let's run it and see what it does. Okay? So what it gave us back was what? How many phone numbers each person has. So rather than display phone numbers here, it's displaying how, it's counting the phones by person. Okay? So, I'm not trying to make you SQL experts. You can live a happy life without understanding group by. But if you're ever doing SQL and you realize, you know, I don't want, I want to combine information rather than see all of it. That's what group by is for. You can look at it in more detail. Yeah?
How does that query run if you just delete group by? What's different?
If I don't use this here,
Yeah.
then that count won't work. So if I try to check this, I'll just run the check here. Phones.cardnum is invalid because it is, well, it's basically, I'm not making much sense of that error, but you can't do a count. You can't have a count like that unless you have a group by. It has to know what to count. The group by tells it what to count. In this case, it's counting. It's counting rows where the card number and the name agree. Okay? Let's look at another example of what's possible. That's the same thing, except I'm ordering it differently. Okay? Here's some more SQL that's going to be useful to know when you're writing your program. What do you suppose that does? Okay? That actually changes the database. That's an insertion, and that inserts into patrons Marley as the name. Okay? So let's execute that and see what happens. Wait, okay. Like I said, it's not a stationary database. I've got to copy it and paste it into, I've lost the place I want to paste it. So I'll paste it there and we'll execute it. And so it's telling you that it added a row to the table. And now if we do something like select star from patrons, we'll see that now there's a new row called Marley with card number 10. Now where did the 10 come from? Yeah?
It's a sequence, you can't see if you deleted rows.
Well, okay, so what kind of column is card number? What does this reveal about the card number column? It's auto increment. You might wonder, if the last is 4, why did it produce a 10? And the reason is I've been using this database for a couple years, and first time I used it and I added Marley, it added it as row 5. And then I went back and deleted it. So it just gets the next unused card number. And 5 through 9 have been used in previous demonstrations. So insert is how you add a row to a database. You'll certainly be doing that in your Boggle server. Okay? This is an update operation. It changes a row in a database. So look at that and tell me what you think it does. Yeah?
It changes every row with the name of Marley to
Right.
have a new name.
So it looks in the patrons table. Every row where the name is Marley, it changes Marley to Bungie. I have a couple cats. Those are their names. So it affected the row. And now if we look at the table, another way to look at the table is I can go to phones here and say show table data.
You said cats.
And it showed, oh, that's the wrong table. And it shows that now I've got Bungie on row 10. Okay?
No.
So I don't know that you'll need to do an update. Would you need to do an update? Can anything change? Yeah, I don't know. Okay, and this is how you delete a row. So that just says delete from patrons where name equals Bungie. So delete every row that has Bungie stored on it. Now delete's a dangerous thing, obviously. What if we left the where off of that? That would delete every row. We don't want to do that. We just want to delete So delete from patrons where name equals Bungie. I'll execute that. And it deleted the row. So next time I add Marley, I'll be on row 11. So your experience is going to be tomorrow designing the tables. Next week, you'll be writing queries to do the kinds of manipulations you need, and then you'll be embedding those queries into C# code in place of your poor man's database that you're doing this week. Okay, so we'll continue on with this next time.